So welcome to the Picture Language Seminar. It's a beautiful day today, the Harvard Wellness Day. So we have very nice weather, and that means there are no classes, but we have our seminar, and we're very pleased to have in our oscillation between mathematics and physics, one of the best experimental physicists, Mikhail Lukin. He's going to tell us about what he can do with his 200 qubit two-dimensional array to explore new scientific frontiers with programmable quantum systems. So Misha, why don't you share your screen?
Thank you, Arthur. Okay. So do you see it?
Beautiful.
Okay, so thank you very much, Arthur, for kind introduction. So it's a great pleasure to be here. So it's kind of maybe a little bit of a change in terms of the type of talk. What I'm going to talk today at the seminar. I'm going to talk today about our efforts to build quantum machines, and basically, this is what I view as a quest for controlling quantum world, where we are trying to isolate and control simple quantum objects and build more and more complex systems from them. And what we're trying to do, as you hopefully will see, is we are trying to basically try to explore new physics with these engineered many-body systems, and in particular create and probe new entangled states of matter, but also explore new applications. And the applications, of course, something that you kind of hear a lot about in the news these days. So actually, despite of the fact that the subject of quantum is very much kind of now, there's almost every day some major new announcement, it is kind of at an interesting juncture. So despite all of this excitement, I'd say it's really not clear right now if and how we can build truly large-scale quantum systems, composed from thousands or millions of good qubits. But even more surprising, perhaps, is that if I were to, for example, build today a huge quantum computer, and I were to give you this computer, you would actually not really know what to do with that. So, these are these two kind of big questions in the field: how to build large-scale quantum systems and how to apply them to kind of obtain meaningful quantum advantage. So kind of the state of the field, I would like to kind of sometimes summarize in terms of this ultimate quantum rivalry, and you can think about it from different kind of perspectives, from your favorite perspectives, but I would like to take a little bit kind of broad philosophical, maybe a little bit Eastern perspective. So this rivalry here is actually not between different platforms or between different countries, but between two competing forces of nature. And one of these forces is what I would call controllability, and another one is a scalability. So what I mean by that is that, for example, if you take a group of smart people, like for example, mathematical physicists, and put them in one organization, if they are truly brilliant, this organization almost by definition will be very hard to control. So and it's like that in quantum world as well. So basically, if you kind of start putting more and more qubits together, they actually just become much harder to control. So, and basically kind of bridging this gap is really what is now a central goal of this field. And the current frontier in the field is to really kind of build machines which can do kind of interesting and useful tasks, with systems, of something on the order of 100 qubits or more, and then use these insights to build, still bigger and better quantum machines, and perhaps start to explore, and test some useful algorithms and perhaps some scientific applications. And what I would like to really kind of hopefully convince you today is we are entering this kind of age where this is actually possible. And we are now, kind of starting to kind of really explore the systems for kind of new discoveries, kind of explore new kind of applications which are very much scientific. So I'd like to kind of call this the age of quantum discovery or era of quantum discovery. And I really want to convince you towards the end. I hope that we actually already have kind of entered this era. Okay, so what I really would like to talk to you today is shown here. So I want to focus on one basically specific set of projects in my group in which we are trying to build quantum machines starting from individual atoms which are suspended in so-called optical tweezers. And I will tell you about how we can kind of assemble quantum matter atom by atom in these systems and then use it to start explore quantum phenomena like quantum phase transitions, various kind of spin models, quantum dynamics. And then as an outlook, I will also tell you about how we are kind of now using this machine to explore, for example, topological matter, for example, spin liquids, and also making some first steps towards quantum optimization. Okay, so in our experiments, we are using individual neutral atoms. The reason why one would think it's a good idea to use this kind of systems is because they are known to have excellent coherent properties. So, for example, optical atomic clocks, which is sort of the most precise measurement instrument created by humankind, is based on neutral atoms. And it's actually easy to create a large number of neutral atoms. So around in each and every one of our room, there are a lot of atoms flying around. But at the same time, there are also challenges. And the first challenge is that the atoms in a gas phase interact very weakly. And the second is that all of these atoms which are flying around us, it's impossible to control. Basically, because in particular, it's just impossible to even follow each of these atoms. So neutral atoms are hard to control individually in large numbers. So motivated by these considerations a few years ago, we started thinking about a new approach of building scalable quantum systems. And the idea here is the following. So we start with the low pressure gas in a vacuum cell. And we cool this gas by using lasers. These are kind of techniques which have been developed in our community over the last several decades. And then we start with this gas of pre-cooled atoms and shine the tightly focused laser beams. These are the so-called optical tweezers. So each of these laser beam attracts atoms to the point of their highest intensity. And we focus these beams so tightly such that each of these tweezers can host at most one atom. But what we do in practice, we don't start just with one tweezer. We start with hundreds of these tweezers and try to load them all simultaneously. But then, what happens is that the system still has entropy. So basically, some of these traps get loaded and some are not, some are empty. So to get rid of this entropy, what we do, we simply take a picture of the atoms, figure out which traps are full and which are empty, and then remove the empty trap and then rearrange the remaining atoms in the desired configuration. With that, we end up with these regular arrays of atoms, which are spaced by several micrometers. So atoms in those traps, they don't talk to each other. The interaction is negligible. To induce some interaction in a controlled way, what we do is we excite them into the states with the high principal quantum numbers, the so-called Rydberg states, where atoms really kind of orbit, in the large orbits. And then what happens is the atom size becomes very large, and then the atoms start really talking to each other. And that way we can really engineer the interaction. And so that's our approach. And this is a collaboration with two of my colleagues within our Center for Ultra Cold Atoms, whom most of you, of course, know is Markus Greiner and Vladan Vuletic. So this is the first generation of our experimental setup. It's almost historical now. So the key element here is this device called acousto-optic deflector. So it's a device which takes as an input a laser beam and several tones of radio frequency radiation. Then each tone basically deflects this laser beam by a certain angle. So this is actually a device similar to that one used in the supermarkets for barcode scanners. You probably have seen it. So basically, in this way, what we can do is we can start with a single laser beam and create this kind of line of light beams. These are our basically tweezer traps, which we then project into the vacuum chamber. And then we have another objective where we can detect the atoms and basically, activate this feedback system, basically remove the empty traps and, rearrange the traps. So basically removing the trap simply means that we should take one tone away, basically just eliminate it. To scan the trap, you just chirp the frequency of this radio frequency tone. And so this is also the first generation of students and postdocs. So some of them are still here, and I'll show you the picture of the new generation. So as I already mentioned, what we do is to control interactions, we excite atoms coherently into the Rydberg states. And we like these Rydberg states for two reasons. First, they have a long lifetime, so over 100 microseconds typically, and also very strong interaction. So in particular, the interaction scales as 11th power, asymptotically as 11th power of the principal quantum numbers. And for example, the van der Waal interaction between two Rydberg atoms in the state n equals 100 is 14 orders of magnitude stronger there than the van der Waal interaction between the ground state atoms. So the 14 orders of magnitude is a big number, and we could make good use of this number. So one specific concept that I would like to kind of introduce here, because it will be used throughout my talks, is a concept of the Rydberg blockade. So the idea is the following. So suppose you try to drive these two atoms resonantly to the Rydberg state. And if these two atoms are far away, these two atoms will just undergo radio oscillations independent from each other. However, when you start bringing atoms closer and closer together, what will happen is that eventually this strong interaction will take over. And what it means is that the state where both atoms are excited will be just shifted way out of resonance. So what it means is that basically past certain distance, we are going to call it blockade radius. What happens is that you will be able to excite either of two atoms, either one atom or another, but never both. So that's the idea, the concept of the so-called Rydberg blockade. And this is something that we've developed almost 2 decades ago already now, but it's actually, we like this approach very much, because it allows us to entangle atoms, perform quantum logic in a way which is extremely robust. It's insensitive to motion, to exact positions of atoms, and etc. So in short, what we'll do is we'll start with the disordered array of atoms. We will then prepare some kind of position atoms appropriately, and then we'll subject these atoms to sequences of laser pulses, and then after that we just will detect the state of the atom. So there are many kind of different directions where you can apply the system. This talk will focus mostly on the idea of applying them to quantum simulations, and kind of this idea comes from Feynman. That was actually the original, one of the very original ideas which motivated this entire kind of direction of quantum computers and quantum simulators. And the notion is that simply that if you have basically, n qubit system, then simulating this kind of dynamics, is actually, at least exactly, is very hard, because you need to solve, to the LON coupled equations. So alternative approach, we can try to just implement the kind of desired model on our programmable quantum system, and then using standard set of, for example, qubits with interactions, and then try to basically just mimic or simulate this dynamic. So basically, this is exactly the picture which I will kind of try to kind of use to illustrate. So we will arrange the atoms in a certain way. We will kind of engineer interaction. We will, engineer the way how we actually, let's say, excite these atoms, and then we will try to kind of see what's the answer. So the simplest example of this quantum simulator is the situation where you basically have just one-dimensional chain of these atoms. These atoms, for example, are homogeneously excited to the Rydberg state. This system is described by this relatively simple Hamiltonian, which actually can be mapped to Ising Hamiltonian. But let me kind of just, illustrate various terms in this Hamiltonian using the ground state kind of phase diagram. So first off, suppose the interactions between the atoms are negligible. So then everything that the ground state is basically determined by the sign of this term. This is a laser detuning, which is also like a chemical potential. So basically, if this detuning is negative, that means that, basically, all atoms should be in a kind of electronic ground state. But if the detuning is positive, then, you want n to be 1, right? So that means that all atoms must be in the Rydberg state. So these are the two configurations. But of course, once you turn on the interactions, then this Rydberg blockade, which I just described, does not allow us to excite all atoms, right? So for example, if blockade extends just to the nearest neighbor, then the state that we will excite will be the state up, down, up, down, up, down. So basically, it's a state which features antiferromagnetic order. So in other words, it has Z2 symmetry broken. So if we go now to even larger interaction range, then, we will be able to excite only third nearest neighbor. Both first and second nearest neighbor will be blocked, and so on. So these are these kind of ordered states which emerge. And we can actually exploit this phase diagram and explore this phase diagram very easily by just starting with atoms in the ground state, adjusting the interactions and positions of the atoms, and then just try to enter this ordered state. So, and this is what we have done a few years ago. So here is an example. It's a 13 atom chain where we first start with atoms separated very far away. And then in this case, we enter this state, this antiferromagnetic state, up, down, up, down, up, down, up, down. And if we bring the atoms a little bit closer together, then, two of the nearest neighbors are blockaded. So then, it's up, down, down, up, down, down, etc. And this continues. So basically what, in this very simple example, you see is that by programming the interactions, we can, for example, engineer the desired symmetry breaking. We can really kind of explore different phases. But the beauty of that is that you can, go very easily, basically from a system containing few atoms to a system, to a larger system. So this is, a 51 atom array, which we explored again a few years ago. So here is a picture of 51 atoms. And before we do any kind of Rydberg excitation, and then we, for example, do this kind of adiabatic transition into the ordered state. And so, what in this case we observe is something what's shown here. So we don't always see the array completely ordered. So in most cases, we see this kind of like ordered chunk, up, down, up, down, up, down. But then there is some kind of defect, and so this defect is a domain wall. So, and actually we can explore now this domain wall. So we can study, for example, the average density or variance and so on. And actually what we see is that if we go across this phase transition, basically this average density of domain wall smoothly, goes from large number to small number, but the variance sharply picked, is sharply picked. And so basically what it means is that really the system at this point does not know which state to choose. That's why this kind of variance, fluctuates. And, this is how, for example, we can actually identify the phase transition. And by the way, for this specific model, this phase transition was predicted by Subir and his collaborators. And in fact, the predictions were in quite good agreement with what we have measured. But we can also look at this system in a different way. We can also look at it microscopically. We can basically just look at all of these snapshots and analyze and ask, for example, what's the most probable, atomic arrangement that we create. And so in this case, there is one state which stands out, and this is this perfectly ordered state. And in our early experiments, this state occurred with a small probability. We since then improved our system quite a bit. And for example, in a system of this kind, we can now hit, this grounds. We can prepare this ground state with basically, with substantial kind of double-digit percentage probability. We can also look at this. We can also look at these images and basically calculate any kind of, correlation function. So, for example, this is a density correlation, which is basically corresponding to antiferromagnetic state, is up, down, up, down, up, down state. So, and from here, for example, we can extract things like correlation length and so on. So basically what you see is that we have a wide variety of tools which really allow us quite unique insights, unique peeks into this phase transition, and in particular, dynamics. And, this is something that I will talk about in the rest of my talk. So by using this approach over the last few years, we actually enjoyed,
Can I ask a question?
Yes.
Mr. Zhenghan, can you go back one slide?
Absolutely, yes.
So, in your system, you have all those. I assume the red circle is the excited state, the blue one, well, the green one is the ground state, right?
Yeah.
So, I think you can measure some kind of density correlation. So, at a particular moment, do you think they are really in superposition of many different patterns, or is a single, configuration of your atom?
So from this specific image, you cannot say that. So what you need to do, you need to basically kind of change the atomic basis and then measure in different bases.
I see. So
and in fact, so I can show you, maybe it's kind of the answer is in the next slide. So we, so like some of the experiments we have done, and I'll talk about the other things. So one of them includes this kind of probing this entanglement. And actually, this is, for example, this was an experiment where we, did something what I just showed before, but in 20 atom chain. And there we prepared really a cat state. We prepared a state which is, up, down, up, down, up, down, plus down, up, down, up. And not only we prepared it, we verified it. And we did it by looking at this probability of kind of seeing these states in one basis, but then we also rotated the basis and we saw, look at some other observables, in that case were parity. So basically we can also, verify that we have a superposition state, right? By just by making measurements in different bases. It's like for qubits would be Z basis and X basis. Does it make sense?
Yeah, okay. Maybe I can just tell you what I'm thinking. So, when you show me the picture, it's reminding me, people study quantum Hall states, fractal quantum Hall, like 1/3 means like, 1 in 3. So that's very much reminding me of that picture. So if you can make them in superposition, whether you can simulate, kind of a quantum Hall state in this kind of,
I think this will, something like that, will come towards maybe the end of my talk. So but basically, I mean, that's what's kind of special. We can look at this system. I will look at it as a kind of many body kind of system where we look at macroscopic observables, but we can also look at single particle observables. We can extract things like entanglement.
I see.
We can use this system to, for example, using the similar approach, we have carried out like high fidelity multi-qubit quantum gates, where you can basically entangle many atoms at once. We have studied these different phase transitions. We measured, for example, critical exponents for these different transitions into this. And we also have studied, dynamics. I will actually also talk a little bit about that. So,
thanks.
So I mean, the point here is that these directions are really very closely connected. So they all involve, coherent, either analog or digital evolution, or a combination of this. Okay, so fast forward in 2020, about a year ago, we have actually completed a major experimental upgrade. And so in this upgrade, we now use this device called special light modulator to basically, create a computer-generated hologram to create now two-dimensional array of optical tweezers. So this is, for example, a type of array which we were working with. Now we can easily create thousands of atoms. So one question is, how do we sort atoms in this kind of arrangement? So actually, the way how we do it is we now have two acousto-optic deflectors. It's a separate channel, which we superimpose on these traps. And basically, one of these acousto-optic deflectors can move the atoms in a vertical direction, and another one in a horizontal direction. And so these are all computer controlled, and we can actually do it in a very fast time scale. So there is one other thing which happened around a year ago, and this is an exemplified this picture, which actually I was thinking that maybe it's an anniversary. It's just one day to this anniversary. So this is a historical picture. This is the last day where all of the group members, actually, even this time not quite all. There are some of them already on Zoom, but they were in the lab. So basically, this is the week a year ago. So we were kind of told that our labs will have to shut down. So and the only thing which can operate are servers. So, this experiment, which I just described, has been converted into the server, and actually it has been operating nonstop, for the last year. So everything what I'll show you from now on, the data has been taken basically remotely in the last year. And yeah, it has been quite a year. So I think maybe it's time to pause here a little bit. So there are some remarkable people who have done remarkable, work, not only those people who are shown who are very special, I must say, but a lot of other kind of members of our community. So yeah, and the mathematical picture language seminar now is a worldwide phenomenon. So yeah. Anyway, so this is kind of the type of systems which we are now working on. We typically load about 600 traps, and sort the atoms. We can sort up to about 300 atoms. So this is a kind of somewhat slow version of what's actually happening in the lab. So basically, we can fill each trap with more than 99% probability. So and let's see if this that can work. So and basically what it means is that with some reasonable probability, we can, prepare arrays up to about 300 atoms. So, but what's kind of nice in this 2-dimension, we can now play with geometry. We can prepare basically any lattice that you desire. So, for example, we can also prepare arbitrary patterns. So this is just the pattern we kind of dialed on a computer, and then we just press a button, and basically we have atoms located in this this position. So yeah, so basically this is now kind of an interesting playground, and let's see what we can do with that. So the first thing what we can do is just try to see if we could extend these considerations which we've been talking about, including phase transitions, into 2 dimensions. And the simplest kind of scenario here is to have atoms arranged in a square lattice. So basically, if you have just short ledge blockade, just the nearest neighbor blockaded, then what the kind of state that you will naturally create is an antiferromagnetic state. So we call it a checkerboard phase. Basically, every other atom is in a Rydberg state. But of course, if you start kind of increasing the interaction range, then you will start creating different phases. In fact, it turns out that there is a whole zoo of the phases. There are some of them quite intricate. So this is actually a phase diagram which has been calculated by Ryan, one of the students from Subir's group. I'll have his picture later in my talk. And basically, it was kind of clear for us that we can really now access this quite complex phase diagram. But even this transition, the simplest transition into this checkerboard phase, it's actually known to be a 2D or 2+1D Ising quantum phase transition, has apparently never been observed. Okay, so let's see what we can do about that. So we can just prepare the atoms in this kind of regular square lattice arrangement. Start turn on the light with negative detuning, and then just try to basically enter into this ordered phase. And indeed, we can just, in this case, it's a simple ordering. We can just look at this picture and see that we have created a desired state. So again, not in each shot we create a perfect antiferromagnetic path. So we can quantify it by using either this correlation function, this density correlation function, and we see that this correlations extend over the entire array. Or alternatively, we can again look at this system microscopically. And again, there are two most probable states which occur here. These are these two kind of different antiferromagnetic states, right? So we can actually, for example, ask, what's the probability that we actually create this ground state? And in fact, this probability scales exponentially with the number of atoms. But this number here is quite close to unity. So basically, from here we can really benchmark our system. We see like up to 3% error per atom, but with correlations basically extending over the entire array. So there is one question that one can ask is, okay, is this system dynamics, quantum or classical? And that's a valid question to ask. So in order to answer that, one actually elegant way is to really study the nature of this transition. So, and in particular, as already mentioned, quantum mechanically, it is expected to be an Ising, 2+1D transition, which is actually characterized by these critical exponents. And actually, one of them is dynamical critical exponents. It should be one because it's basically a transition described by relativistic field theory. And another one is this correlation length exponent, which is actually has a non-trivial value around 0.63. So the way how we can actually study that is by going across this phase transition at a different rate. And at this point, we exploit something which is called quantum Kibble-Zurich mechanism, which basically connects, these dynamics across this transition to this universal scaling exponent. Specifically, if you go quickly across the phase transition, you create, very short correlation, so a very short range, like it's shown here. If you go slowly, then the correlation length expands. So this is actually quite dramatic when you try this out. So then what you can do, you can just plot this correlation length as a function of the final point and also as a function of speed. And what you see is indeed for slower speed, the correlation kind of length grows largest. So how do you extract critical exponents? For that you use this idea of universality. So close to phase transition, the universality tells us that basically, all curves should collapse under appropriate rescaling. And, this rescaling allows one to basically extract these exponents z and mu. And indeed, when we do this rescaling, we find that indeed curves quite dramatically collapse on the top of each other. And actually, by optimizing this collapse, we can extract with this critical length exponent mu with actually a precision of the second digit. And it's very much in agreement with this prediction, with this quantum prediction. Is actually different from, for example, classical prediction would be that it should be 1. So from that, not only we can actually, say that we have, we can observe and study this Ising quantum phase transition, but we can also benchmark quantum many-body dynamics. It really proves that our systems becomes quantum mechanically, and this is actually not easy to do. So in fact, people tried to do it on systems like D-wave machine, and it's actually did not work. Okay, so with that, what we can now do is we can start basically exploring this phase diagram. And actually, I don't think I should go into much details, but in addition to the checkerboard, there are these phases with different ordering, the striated phase, the star phase, and we basically observed all of these, phases on the lower part, at least, of this phase diagram. We were able to study them and quantify, and actually even study quantum fluctuations in those phases. And this we can also experimentally map those diagrams. So basically, I mean, this is like a new frontier. We can now exploit this, and explore this system. So this is a little bit of our current efforts. So I'd like to give you now a sampling, so I don't know, maybe it's a good point to stop here and ask if there are some questions about the system. So what I'd like to do is basically give you a little bit of a kind of a sampling of the current, projects, but, maybe it's a good time to pause briefly and see if there are any questions.
Oh, I do have a question if you read out. So, ideal, well, I think
why don't you turn on your video when you ask the question so we can see you?
Oh, sure.
Yeah.
I mean, sure. So, I think it's the realistic Hamiltonian. So you have the 3 parameters: omega, delta, and this V alpha or VIG.
Exactly.
I think you said before VIG is basically like a array of either 0 or infinity.
Yeah.
And then I assume the omega is the energy between the ground state and the excited state of a Rydberg atom. That's the omega?
No, so basically
maybe they are exactly. That's my question is, what's the physical implementation of omega, delta, and how independent we can get them?
So omega, it's very simple. So omega is actually a square root of laser intensity. Omega is a Rabi frequency. It's like transverse field, basically. It's like transverse field, but it's proportional to square root of laser intensity. That's omega.
Okay.
Delta is laser detuning from resonance. And finally, this VIJ is basically the interaction. It's actually a van der Waal interaction. So, this kind of just, on and off is an approximation. It actually turns out to be pretty good approximation for many purposes, but in principle, you have also this R to the 6th power tail. So,
okay. Yeah. So how independent is omega and delta I can assume? Are they related, or can I assume, in the 2-dimensional plane, I can take any, 2 number I want?
Yeah, so omega and delta, anything, yeah.
So,
and, right now, the limitation, or at least in what I showed you, is that, basically it's uniform across the array. Omega and delta are the same.
Okay.
But we can also make that atom dependent, and we have done it, and we are doing it in some experiments. Yeah.
I see. Okay, thanks.
But it can be anything, in principle.
Great. Okay, thanks.
Okay, so let me then give you, unless there are other questions, let me give you a little sampling of the kind of projects which we are working on. So let me start with this project of kind of non-equilibrium dynamics. So this is, I think, maybe the kind of most, fruitful, if you want, frontier of these programmable quantum simulators, because basically what we can do with these systems, we already now can take, all of you guys to the corners of Hilbert space where no one has ever been. We can create the states which no one has created, and we can just see what is there, right? So, and this was actually a very first, one of the very first when our atom array started to work already in 1D. We just kind of started playing with that, and one of the first experiments we have done was like this. So suppose we do this kind of adiabatic transition into antiferromagnetic states, is up, down, up, down, up, down. And then afterwards, and we do it smoothly, and then afterwards we kind of abruptly change this detuning just across the phase transition to 0. And our idea at the time was, let's study how the system thermalizes. And what we have seen, is indeed, initially you have some order, which then, after you have this quench, this order disappears. But then, sometime later, this kind of complementary order appears. Then it disappears again, and then this order appears again. So basically, these correlations, seem to oscillate after this quench. And initially we thought, oh, this is a 5-atom system. It's a small size, it's probably a finite size effect. But then we started looking at larger and larger system, and this effect did not go away. So basically what happens is that, after you quench, you have this, some correlations, which disappear and then, they revive, disappear and revive. And actually at the time we were quite puzzled. So at the time when we published this, it was our 2017 paper, we did not really understand, what is kind of going on, because in particular, this is a non-integrable system and, it should formalize. And it does formalize eventually, but, it formalizes kind of very slowly. And so basically, so this experiment, I think it's one of the first discovery made with the quantum machine. And actually it really inspired, theorists to really think about new concepts. And actually it turns out that this kind of inspiration, is in principle not that far away. So for that, we'll just have to cross Oxford Street, it turns out that, this kind of phenomena related to something which is called quantum scars. So quantum scar is something which our colleague Eric Heller concept he's developed in this context of single particle, quantum chaos. The idea is basically the following. So let's take some, chaotic classical system like a billiard. So in this billiard, most of trajectories are completely chaotic, but there is a small number of trajectories which, form this kind of closed loops. These trajectories are not stable. And you would think, well, if you quantize the system, they just shouldn't matter, right? Because uncertainty principle will lead to basically kind of washing out everything. But actually, it turns out not to be the case. Under certain conditions, these trajectories basically result in the quantum eigenstates, which kind of resemble them. So that's that was a kind of Rick's idea. So these observations, which we have kind of reported here, turns out can be connected to this quantum scars in the following sense. So basically, it turns out that these trajectories corresponds to very special initial states of the system. So most of the states in the systems are completely chaotic, but there is some special states which form this kind of regular band of energy, which result in this kind of revivals. Or alternatively, if you think about this system from the point of view of matrix product states, you can actually construct low bond dimension matrix product states which have exactly this kind of closed unstable trajectories. And so basically this kind of experimental and theoretical work really stimulated a large body of work. So there is almost still up to now, like every week, there are a couple of papers on archives offering another kind of explanation of that. So it's actually two people who really contributed early on to understanding is Hannes and Sunwon. Sunwon actually is joining MIT this fall as a faculty member. So, what can we do with this system? Now we have a two-dimensional array. We, of course, can try to see if we can create these scars in 2 dimensions. And so we will do exactly the same thing. We will prepare some antiferromagnetic state. So in this case, I guess it's a honeycomb lattice. And then we will just quench close to resonance and see what happens. So while initially, once after you quench, this order completely disappears. Then you wait a little bit and then it revives. Then it disappears and it revives again. So it's actually quite striking. And in fact, what we've seen, we can look at it in different ways. For example, you can look at sublattice magnetization here. But it actually turns out that wide variety of this 2D bipartite lattice support these many body scars. Having seen that, we started to wonder, can we somehow engineer the system to try to stabilize these scars? And we made one more discovery. So what we have done specifically is that instead of trying to quench to this fixed detuning, a fixed chemical potential, we quench to the detuning where we actually, which we modulate in time. And you can say, well, why are you doing that? Because typically this kind of periodically driven so-called flow case systems, are expected to hit. But there are examples of phenomena where this is not the case. And the most famous example is, of course, something which we also studied in other systems called discrete time crystal. So it's basically a phenomena where you have some observable in a driven system, which revives with the period, which is multiple integer times the period of the drive. So, okay, let's see if this can have an effect. So this is a simple quantum scar. We just quench to a fixed detuning. We have these collapses and revivals, but they decay. But then if we start doing this periodic driving, basically kicking this system, what we see is that these revivals, dramatically increase. And moreover, what we also observe is that this frequency of revivals basically locks to the half of the drive frequency, very much in the spirit of this kind of time crystalline order. So, we have not, once again, when we saw it, we kind of were a little bit puzzled, so why does it happen? So we actually now have better understanding. So I don't think I will go into great details, but actually it turns out that indeed, you can kind of think about this, this stabilization as a kind of a many-body spin echo. But this spin echo is kind of very special. It actually occurs only for some specific initial states, in particular for these antiferromagnetic states. And once you started with the right state, then these are the so-called scarring states. Then basically it turns out that this actually phenomenon is very, very robust. So, for example, in a wide range of kind of modulation frequencies, you have this, locking, this frequency locking. It also, this locking is robust with respect to interactions and so on. And actually, most important, it's a many-body phenomenon. So it basically requires a linear size, of the system of at least like 10 atoms to really kind of result in a robust kind of locking. So this actually we have just last week, put a paper on arXiv, explaining some of these things. And actually it's, looks like it really is this robust stabilization akin to this so-called preformal time crystalline response. So this, maybe just to conclude this section, so this actually is a kind of quite a unique picture. So this is experimental data showing all relevant microstates for the 9-atom chain. And so what we see here is the evolution, of the kind of the bare Hamiltonian, which basically thermalizes, right? So you basically have all of the states now kind of equally occupied, and on the right one is a driven system, which kind of live, significantly longer. But also, if you look at that, system carefully, you realize that not only this driving extends the oscillation, it also changes the trajectory, and it changes the trajectory in such a way that it stops basically uncontrolled growth of entanglement. So this is actually theoretical calculation showing that entanglement in this driven system is kind of much more stable. So it actually really kind of indicates that this is an approach to maybe steering entanglement dynamics. When you kind of venture into this deep corners of Hilbert space, typically you never return from those. So if you start, driving the system carefully, you can really navigate it and kind of control entanglement growth in a special way. So, so I guess I have maybe 10 minutes or so. Arthur, so I have, a few more things I could talk about. So maybe I'll talk.
Yes, just as long as you want.
Okay, all right. So let me talk about some of the current ongoing work. Still, it's work in progress, but we have some interesting results related to probing topological phases. And so, as most of you know much better than myself, this topological kind of emergent phenomenon in frustrated system is actually a very exciting frontier, across several fields of physics. So in condensed matter physics, this has been a 5-decade-long quest, kind of, pioneered by the ideas of Anderson. And it's basically related to the following simple idea. So if you, for example, have a system with ferromagnetic interaction, if you arrange this spin up, this spin down, so this other one, you don't know where to put, the system is frustrated. And that led to this idea of this kind of emergent, spin liquid, behavior, and already kind of, in the early 90s, people like Subir, have been kind of thinking that it should, some of these things can, appear in a, in a frustrated magnetic systems, for example. But then about 20 years ago, thanks in particular to the pioneering work of Alexei Kitaev, people realized that such systems can actually be useful potentially for things like topological quantum computing and quantum error correction. And so that kind of stimulated another wave of excitement. So despite all of that, I would say, there is no conclusive experimental evidence other than in systems like quantum Hall effect, which are a little bit different, of this kind of spin of spin liquids. And, I would say, that, in particular, this, work on this fault-tolerant quantum computing with onion is perhaps the most exciting kind of intellectually, the idea of the quantum information system, and the kind of this idea of toric code. You have basically, some kind of, loops which have this, expectation, non-zero expectation value. So basically, you can think about the toric code as a kind of coherent loop guess. But despite of that, none of these systems have been implemented in the lab. So about kind of a year ago, our theory colleagues, Subir and his student Ryan, whom I already mentioned, and also Ashwin and his postdoc Ruben started thinking about two complementary kind of approaches to realize these spin liquids. And in fact, they showed that, the atoms, when they're placed in either in the vertices of Kagame lattice or on the links of Kagame lattice, this is the example of so-called Ruby lattice, could be a very good candidates for realizing this, spin liquid, in this case, specifically of the toric code type. So during this last year, we actually explored both of these, proposal in quite some details. And so, in fact, we have some exciting, results, and I will actually focus mostly on the second approach here in this talk. So basically, the key idea here is to implement the so-called dimer models. So what is the dimer model? Kind of dimer model is, and how it's related to Rydberg state is the following. So let's consider these specific examples where atoms are placed on links of Kagame lattice, and let's adjust the blockade radius such that, whenever one Rydberg atom is excited, so 6 of its nearest neighbors are blocked. So in this case, it's not kind of hard to convince oneself that, you can at most excite a quarter of the atoms. And, if you satisfy this Rydberg constraint, and in particular, due to this blockade, these atomic arrangements which you can excite can be visualized using this kind of dimer picture. So basically, for each Rydberg atom, you associate a dimer, and basically, this constraint is satisfied, and you have maximal number of atoms if basically each vertex is touched by just one dimer. So this is, for example, a kind of what we call dimer covering, right? And so basically, it's easy for us to, adjust this interaction range and try to basically, enter this transition diabatically, and then this is a kind of picture that we see. So we see that indeed, for most of the vertices, we have basically a dimer covering. This dimer covering is not perfect. So for example, here you see that there is one missing kind of, dimer. Here maybe there is one missing dimer, and etc. But nevertheless, we can create this kind of dimer states. So what's quantum spin liquid? It's, theoretically is very simple. So it's, because you have basically highly degenerate kind of number of arrangements, different rearrangements, this quantum spin liquid should be a superposition of all of these dimer coverings. So the only question is, how can we observe, how can we reveal, and probe such superposition? So, let's try to, explore that. And so the first thing what we do is we basically, do exactly the same protocol as we have, used previously. We just start with atoms in the ground states and arrange on this Ruby lattice and try to smoothly, adiabatically enter the ordered phase. So in this case, we do see that, the average number of Rydberg atoms increases and then reaches this value of 1/4. There is a kind of a little plateau here. But also, if we look at variance, we see that there is a kind of, enhanced variance, kind of here, at this range of detunings before it kind of drops. So typically, if variance would drop, it would mean that you enter some kind of, ordered phase. But in this case, we do not create any kind of obvious local order. So what kind of order we create? So one way to quantify about that is to go back to this kind of toric code and think that we should have this kind of loop operators. So one of these loop operators is actually very easy to understand. So this loop operator, we call it diagonal string operator, is basically, corresponds to the loop which crosses these links perpendicular to these links. And so basically, if you have a perfect dimer covering, and for example, here, if you go around each vertex, your parity of your loop, which is basically calculated as a product of these parities, -1 corresponds to the dimer present and +1 to the empty link, should be -1. And so it's clear that if you go to larger loop, then this parity should be -1 to the number, to the power of number of enclosed vertices. And we can try to really measure this. It's like a Gauss law, basically, in our system. So we can try to measure that. And indeed, we see that this point where, you have these fluctuations in variance in atom number drops corresponds to this emergent parity. So we can actually study it across many other loops. We see that this parity decreases as the loop size increases, but nevertheless, we observe this parity signal from relatively larger loops, which are basically a fraction of our entire, 219 atom array. So we have this string operator, which reveals transition into a dimer phase, but how do we prove that we have a superposition? So it's actually much more subtle. In order to do that, you have to measure off-diagonal string operator. You have to measure the operator which corresponds to basically flipping these dimers around, for example, each single triangle. And so it turns out that, indeed, if you kind of construct this operator X, it would actually, and you look at a loop, that would really probe exactly the arrangement, exactly the coherence between this dimer coverings. To implement, but how do you measure it in practice? That's actually kind of a very non-trivial question, it turns out. Fortunately, Ruben, and Ashwin, came up with this very clever idea, which basically involves essentially collective kind of rotation of each kind of operating on each local, triangle. So it's basically like a free atom, free qubit kind of operation, collective operation, which turns out converts these X strings into these Z strings, which we already can measure. And, the way how to implement it is to just change dynamically the blockade radius. This is done by literally increasing the laser power by close to a factor of 100, which basically then applies a short pulse, which converts these Z strings into X strings and vice versa. So one can see it quite dramatically if you look at parity of the Z string. If you apply this, quench, it was very fast pulse, you see that initially the system, this parity completely disappears, and then at the right time, it just revives. And using that, we can now measure this kind of what we call X parity loops, which actually demonstrates that we have really coherence across these dimer coverings. All right, with these tools, can we now try to see if we have a spin liquid or not? So the idea here is to compare what we observe on open strings versus a closed strings. And this in particular, I think there are at least two people in there. I mean, actually, this is a new field for me. So I believe two, authors of these visionary papers are present in in this talk, which actually is quite amazing. I did not expect that. But so these are these kind of order parameters, which actually, can uniquely distinguish, for example, disordered and quantum spin liquid phase from the solid phase, or disordered phase from quantum spin liquid and solid phase. And kind of the intuition here, if this resonating valence bond get localized, then what will happen is that you will have this basically this Z open string being kind of non-zero, right? But at the same time, if you just have phase which comes from the laser coherence itself, then it's what we call disordered phase, and this X will be non-zero. And basically, we can measure now these order parameters from quite large, from basically from loops extending across a big part of our array. And indeed, we find this regime where basically both of these other parameters vanish, while the loops, of course, are non-vanishing. And that provides us with really good kind of indication that we see some at least onset of the quantum spin liquid state order. So we can do a lot of other things. I think I'm kind of running out of time a little bit, but one of the kind of most intriguing aspects of these quantum spin liquids is of course anyons. So for us, we can actually almost visualize these anyons, in real space. For example, these E anyons are these vortexes which are not touched by any of this dimer covering. And one question is, do these anyons appear at random, or are they appear in some kind of correlated state? So in fact, these kind of considerations can be probed by looking at the string operators and how they scale with size of, for example, perimeter or the or area. And actually, what we observe, for example, for the Z loop correlators, is that for small loops, they actually the area law indicating kind of this picture, this kind of random anyons holds. But when you go to larger loops, we clearly see some deviations from this area law, and basically it kind of indicates that these anyons are at least somewhat correlated over large distances, and we can also extract, for example, anyon density, and in this case is about 10% per vortex. Even more interesting are these M anyons. So I'm not going to talk about maybe too much about them. So basically they are related to phases or in this kind of open Z string. So basically the phase around the end of the Z string here should change. And in fact, we can kind of measure it once again by looking at scaling of this kind of X loop operators as a function of the loop size. In fact, here we observe almost perfect perimeter law, which basically indicates we have a negligible density of anyon. So with all of these kind of considerations, we really can clearly see that we create some kind of non-equilibrium strongly correlated state. So last thing maybe I will talk about today is our first experiments, probing topological properties of these spin liquids. For that, what we have done is we prepared an array with non-trivial topology, basically a little hole here in the middle. And the way how this hole affects things is kind of can be understood by looking at different dimer coverings. So for example, if you look at these two dimer coverings, if you just put them on the top of each other, what you see is that, basically to convert one covering from another, you need to flip these dimers over this kind of closed loops, but none of these loops goes around the hole. So basically these two dimer coverings are topologically equivalent, but these two are not. For these two to flip, one covering to another, you need to basically go all the way around this hole. So basically this is the same topological sector and this is the opposite. And this has some implications. So for example, if you look at the Z string from the center to the edge, it should be -1 for one of these sectors and +1 to another. But of course they should be all the same. So they should be, always correlated. So, what we do in our experiments, we prepare the superpositions of the states. We aim to prepare basically a ground state, which should be degenerate. And in fact, we should be preparing, this superposition of 0 plus 1, so which actually will appear as non-zero X parity string going around this loop and basically vanishing parity string from the Z from the middle to the edge. So I think it's exactly what we observe in this quantum spin liquid region. We also observe correlations between these Z strings, indicating that we're not just preparing the number state. So I think this is all just first kind of peeks into this, topological, qubits. There's a lot of work remaining, and I think, as you see, I'm getting quite excited about it. So basically, this is a picture from the Scientific American, in 2006. I think is a cover image. So I think the artist who's drawn this picture, must have thought that people are crazy, are getting nuts. What is this kind of thing about this knotting, and so on. But now these can all be implemented basically by poking the system with laser beams and moving them around. We can do experiments like this. And I think what is kind of really, special here is that we really get quite unprecedented insights into this topological matter. There are many open questions. We don't yet know and understand exactly the nature of the state that we prepare. We have ideas how to do it, but it's not so completely easy. And most importantly, can one really use the systems to protect quantum information or not? Is still an open question, But, there are a lot of kind of cool opportunities. The key is that all of these ideas that, many of you guys have fought for last 50 years can now really be implemented. You can really touch these things, implement them, and see them kind of in a lab. So I think, maybe I'll skip this quantum optimization part. So let me just go back to my final slide. I hope I convince you that, this is a really exciting frontier. And I think this era of quantum discovery is actually kind of here, So this is the people whose blood and sweat resulted in this work. So thank you very much for your attention.
Well, thank you, Misha, for an absolutely wonderful talk. I'm sure there'll be a lot of discussion. We want to see this quantum computer that you're building.
Yeah. And it's, if everything goes according to the plan, we might even have a machine in a year or so from now that will be actually accessible that can be accessed remotely. So that's so collaboration with a local startup company.
This is great. So I'm sure there's a great deal of discussion. Anybody who wants to ask a question, please unmute yourself or touch the space bar, hold it, and talk.
Hi, I'm sorry. I'm Matthew. I'm a student. I was just curious, where did you get my question is a little bit of a generic one, but I'm just curious, where did you get the inspiration for your work?
Well, it's, from people like you guys, so this is a kind of, maybe this something, we have quite a special community, which kind of spans, traditional boundaries of the fields. And it goes from experiment to theory. And as you see, like with this kind of systems, if we have some good idea, we can actually try it out, implement it very quickly, and it feeds back to theory to develop new ideas. That's what I call the age of quantum discovery.
Thank you for answering.
And we need people like you to fuel that. The younger generation, right? Who are trained, and what's kind of maybe a little bit less clear. So, for example, some of these things like this, you can think about these dimer states as actually as a solution of certain graph problem, So, and it's actually the part which I missed, which I skipped. We're now trying to basically use this machine to, develop optimization procedure for these graphs. So this is a field which spans all the way from like high energy physics to kind of condensed matter physics to quantum optics to computer science and chemistry, right? And I think this is like kind of being fluent in this, and kind of in theory and experiment are very close. It's a very, very special field. And, and I hope that the new generation really of young scientists, which will be really fluent across this field, and it also includes engineering, actually, and things like this. I mean, these are sophisticated systems. They are, among the most sophisticated that anyone has ever built, right? So I think it's a special time, and
Absolutely, yeah, but yeah.
So maybe Jörg or Klaus Friedenhagen, who referred to, have a comment.
Let me just say, first of all, I did not expect you guys will be in this talk. I don't know if Arthur arranged it. So if I said something which was not right, I apologize.
Yeah, I was very surprised that this very abstract work, which we did some almost 40 years ago, is now something which can be realized in practice. That's fascinating.
Yeah, and not only that, it appears that it's quite a unique kind of way to characterize it. It's maybe at the moment our best way to say whether it's a spin liquid or not, right? So,
yeah.
No, thank you. That's,
sure.
That's amazing, actually.
Misha, I actually have one question.
Yeah.
So, what's the boundary condition of your quantum spin liquid? So you basically do perform simulation on specific lattice, and I think on the boundary of the lattice, some kind of dimer. Well, the dimer configuration doesn't hold anymore because there's a lack of atoms.
So it's a very good question. We can actually also probe it by looking, for example, at loops which go from boundary to boundary. And the answer is, for our system, the natural boundary condition is basically, it's a condensate of M anyons, right? So I guess it's E-type. It's called E-type. So it's basically the boundaries. The boundaries act as a condensate of the M anyon. So if you look at a kind of Z loop from boundary to boundary, you have a fixed value, right? So the value of Z anyons is fixed. And in fact, by changing boundary, we can even change the parity. We can kind of trap E, we can trap or, an extra E anyon. So, but what would be extremely interesting, but, for example, if you look at the X loop, then its expectation value vanishes when you go from boundary to boundary. So I think one interesting direction, and that, we can basically see it pretty much directly. So what is maybe kind of interesting potential implication of this question is, can we manipulate these boundary conditions? So I think Ruben has kind of, and in a theoretical paper that I cited, so he has some ideas how to kind of do it by, for example, locally changing, detuning. So it might be possible. We have not yet, we have tried it in experiment only very briefly, but this is something definitely we would like to explore.
Yeah, because in the original Torah code proposal, was that you actually use some periodic boundary condition, and there leads to topological degeneracy and or topological protection.
Yeah. So this is, if you want, so here this example with the hole is the first we cannot create. You cannot see my screen now. I see. But with this example of the hole, so we cannot yet create a torus in our lab. Yeah. But we can create systems with non-trivial topology. And for example, the system with the hole is the first example, of this type. And so basically, we have two boundaries, both are E-type. So it means that they condense M anyons, right? And for example, in that case, it's very important that the string, for example, X string, really goes around this boundary. If it starts in the boundary, in the middle boundary, and comes back to the middle boundary, we see, vanishing expectation value. So these boundary conditions, play a role already, and we see those consequences of those. Yeah.
Thank you. So maybe another question is that I see your last slide. Maybe you say the future plan is to simulate some lattice gauge theory.
Yeah.
And then I basically read a paper from Jianwei Pan's group that published last year. So they actually use some 71 atom simulators. So basically, one atom has some kind of gauge degree of freedom, and one atom has a matter degree of freedom. And I really want to know, then how can you use some Rydberg atoms to simulate
so,
this?
let me just, I will maybe again, if there are some more kind of, kind of theoretically inclined people, they might correct me, but okay, so I can, let me make a statement. So in one dimension, so we say use the one-dimensional system, and in one dimension, a lot of these things are kind of trivial, right? So you can basically, you can rewrite, the, kind of a simple, many body, I don't know, phenomenon, like, in language of this lattice gauge theory. It's kind of like, you can map antiferromagnetic transition into this kind of Majorana fermions, which are kind of non-local Majoranas, right? And so, and in that sense, I think, these things are maybe not so interesting in one dimension. So I can tell you, for example, that one explanation for many body scars is actually very clever. Is kind of like is what they call it like a false vacuum also in a lattice gauge kind of representation, right? So you just basically rewrite your kind of spin Hamiltonian in this lattice gauge variables, and I think it's kind of interesting, but it's not. I mean, both these things are relatively easy to simulate, except for maybe dynamics, but it's just another point of view. But, but like looking at this kind of emergent gauge fields of the type that I've just shown you in 2 dimensions is something I think very, very special. And there are certainly problems. I mean, toric code is one very specific, model where, it just has 0 correlation length, right? And it's exactly solved, but those problems become complicated, very complicated very quickly, and I think that's understanding transitions between these confined, deconfined phases in these 2 dimensions. It could really be a challenge for classical simulators, where I think I really hope we can contribute to that. I think it's much more serious,
Bergman, was that paper you referred to one-dimensional?
Yeah, it is. Yeah.
Okay, thank you.
May I ask one question, please?
Yes, turn on your video.
Yeah, sure. Hello, everyone. My name is Steven, and I would like to ask you about quantum machine learning and quadratic unconstrained binary optimization problem. So have you guys tried to implement something similar to D-Wave or QAA approaches, maybe based on 2-dimensional tensor networks, which for me it's like quite similar to projector entangled pair states, which can be optimized using classical computer, but nevertheless, can we use such system in order to implement some non-trivial quantum machine learning algorithm based on your experimental setup?
Yeah, so we are definitely, this QAA, I mean, it's the last part that I skipped a little bit. We are, this is definitely, something that we are, like it's on our menu. So I can tell you that we started, we kind of started exploring, both what we call quasi-adiabatic approaches and QAA type approaches. So we are kind of specifically, focusing on the class of problems, which are related to something which is called maximum independent set. For us, it's, relatively easy to implement. And it's, what we call hardware efficient. And we have some promising results. Stay tuned. But, but that's...
Yeah, okay.
But,
sure.
but again, again, so these are, okay, so maybe for others, so these are like, I mean, as far as I understand the question, so there is this class of these heuristic algorithms, which, we have some ideas why they could be used to, for example, outperform, classical optimization or classical methods, but we don't really know, right? There are no proofs. And so in that case, what is the unique opportunity here is that we can now, try these things on coherent, 200 plus qubit machines, right? And
it's very amazing.
and I mean, but I can tell you, for example, that so we have some results now, but we are still trying to understand. It's like you benchmark compared to what, right? I mean, we cannot yet solve NP hard problems. I mean, and the graphs will look.
Yeah. Okay.
We know the solutions, but I mean, but we are now starting, so basically developing intuition, which kind of graphs, for example, are hard classically, but maybe easier quantum mechanically, which graphs, are easy classically. I mean, that's our hope, to basically be able to sort this out. And I hope this would help also to the, this machine learning task. So I should say that there is one other kind of machine learning task, which is purely quantum, where actually, where you really need to use quantum device. And this is something, we had a paper a couple of years, on this what's called QCNN. And you can use some of these things, for example, to do things like quantum phase recognition.
Mm-hmm.
And that's something we're also looking now very kind of carefully at, in particular in connection to these topological phases, right? Where we can improve our characterization, where basically, the idea is whether we could essentially find, better observable, where we can outperform, famous BFM,
Yeah.
by using quantum machine, right? I mean,
Thank you very much.
So are there other questions? Well, I think we should thank Misha again. Oh, Benkhan, you have another question.
I think it's relatively quick. So Misha, I have a relative technical question. So you said that for the Hamiltonian, the omega term is roughly like a transversal Ising.
Yeah.
So for the realization of toric code, so toric code is time reversal, parity reversal. It seems like that term might break the symmetry. That means in your real experiment, that term is really small?
No, I think maybe, okay, so maybe this is something we should discuss offline. But so what happens is that you basically, well, you can, for example, see this, if you want to kind of, try to derive, something like the, this, operators which, correspond to like flipping around hexagons, right?
Mm-hmm.
So it is indeed true that that this detuning should be larger than omega.
Okay.
Right?
Okay, I see.
But it does need to be much larger, right? Right. So, but all, I mean, I should say from point of view of symmetry, all kind of observations which we have now are very much consistent with the Z2 spin liquid.
I see.
It should have exactly the right property as toric code, And actually, we are now still working on it, but I think we believe that there is a kind of rigorous mapping of toric code to this. So I'm actually quite convinced we will.
Okay, I see. Because I'm ask you the independence, because I'm thinking maybe the delta omega is like in the fractal quantum Hall, it's like a fading fraction or something. So if you go really they very different, I'm thinking you might get chiral phases rather than.
I believe there might be an opportunity for chiral phases.
Okay,
but one probably needs to do some, add some other ingredients, to the, but yeah.
Yeah, that'd be more exciting.
Yeah.
Thanks.
Okay. That sounds good. Yeah.
Well, thank you again, Misha, for a wonderful talk, not only for your beautiful experimental results, but also for the interesting questions you've posed for theorists. There's so much that can be done.
Sounds good. So I look forward to, a new generation of questions, which we can hopefully answer together,
Yeah, thank you, and see you next week. Bye-bye.
Thank you.
Bye-bye. Bye-bye.